Narayan is here? Not yet. Very quiet, almost like a funeral. I mean, folks, come up front. I mean, young people can sit down here on the carpet. It's very nice. Come on. It's supposed to be an evening talk. Class time is over. Now everybody has to relax. Yeah. Come here. You have to come here because it's you're chairing the session. Okay. You can tell all those kids to come up. You can come and sit here. Good. There's a chair right here that's not occupied by anybody. Yeah, this one, black one. Yeah, Ravi, you're chairing. This time, yeah. Yes. Yeah.
Okay, anyway, let's
Yeah, come here.
Anant?
Yes.
I'm sorry, I got
Yeah,
stuck
yeah,
actually.
here's the camera.
Okay.
Yeah.
So let's welcome Anant. Anant is, Anant doesn't need any introduction to physics community. A very eminent physicist, has done wonderful works, produced a lot of great students. And today is going to share some of his, experience and outcomes.
Yeah.
Thanks, Anant.
Yeah. Thank you very much. It's a great pleasure to be here. I was here in September. I was a victim of the hospitality of Bidango, who was convening a meeting of the India CERN task force, of which I'm a member. And this time I'm a victim of the hospitality of Narayan. It's wonderful to be back. So I was very excited to hear about this workshop, and a school, which is primarily a pretty technical school. So I thought that perhaps I could give a talk that would lighten the mood, especially in the evening. I also had a technical talk prepared, but I thought 2 talks would be just from me would be just too much for the audience. So part of our group's technical activity will be reported by some of our co-workers later in the day. So this is, of course, the NISER, which is one of the flagship educational institutions in the country, and it trains all of you in the basic sciences. So, and many of you are very young, you're just out of school. So perhaps you're also wondering, what are you doing in this field called science, and what is the nature of this particular enterprise? So as I plan to enter the 7th decade of my life in the next few months, I thought it was a good time for me to summarize what are my thoughts about a life in science. Not a terribly distinguished one, it was an exaggeration by Ravi over here. So, but I thought that we should talk to the younger generation about why we do science, so that, this tradition can go on. And India has, of course, been having modern education now for well over the century, and there are many distinguished scientists who have come from this land, who have worked in this land, who have worked in other places, and so on. So on the one hand, I want to talk about the universality of the experience of science, and also on the other hand, talk about the particularities of doing science from a developing country. So I have a very large canvas over here, so I don't know which part of this canvas I'm going to color, but I hope that you will bear with me as I go through this and talk about what I think is the experience of science. Most of the talks today have been pretty hard, pretty technical, so this will be the exact opposite. It'll be like, you know, a very gentle introduction to many ideas from many different branches of science. And even in such a talk, there's a little bit of what I might call cognitive stress. Those of you who are from biology will have to devote a little bit of attention to ideas of physics. Those of you who are in physics will have to think a little bit about biology and mathematics. So it's not like watching a sitcom. I hope that's a little more than that. And I also hope that every one of you will carry something away. There are eminent international experts over here. So obviously, many of the things that I'm going to say are not going to be very impressive for them, but for them, it is an experience to be here in our country and to see many different developments. They may not be as aware of the history of science in this country as many of us are. So perhaps this would also be an interesting cultural experience for them. So I'll be talking about many of these things, and I do hope I'll go reasonably fast through this talk, that we'll have enough time for questions and discussions. And I also talk about some of the social dimensions of science. As I said, this is about doing science in a developing country. It's also about the changing era, about issues that are prevalent in every single culture, for instance, about the representation of women or representation of underprivileged communities. How do they enter this enterprise? So there is, as I said, it's a broad canvas. So many of you who are going to be in science, I'm sure your parents are worried. Why did you choose this path of science rather than being in engineering or becoming a doctor or a chartered accountant and so on? So many of us will be martyrs. Some of us already are, but I hope that none of our sacrifices will be forgotten. And so this is to all of you, that should you become a martyr to knowledge, don't worry, your sacrifices will not be forgotten. So I want to start with the words of a very famous person, David Hilbert, who was a great mathematician of the late 19th century and part of the 20th century. He had this iconic words as to why one does science, why does one do mathematics. So these words I love very much. Of course, this is the English translation, and they're actually written on his tombstone also. So he said, we must know, we will know. That is, it is an intrinsic human desire for knowledge. How do we know this? Well, other philosophers and other historians and so on have all written about it. So we will take this to be true. This is not something that we are going to question, at least during the course of this hour. So as a puzzle for you, I'm going to put up a picture of this person in black and white, and I won't tell you who it is. If you know it, please keep it to yourself, because some of you have heard a version of this talk already, so you already know who this is. But towards the end of the talk, I'll tell you that this is a very famous person, but who is not adequately represented in popular culture, hardly known to the public mind. Let me start with some pretty pictures over here. And this is very fortuitous, because I saw that the snack that you all had is what is called a vada, often called a donut in some other cultures. The taste, of course, is different, but the mathematical structure is the same. It looks like what we call a torus, but this is a torus that is somewhere out in the cosmos. And this is a picture that was reconstructed from something known as the Event Horizon Telescope, which actually is consistent with the existence of a black hole at the center of this picture. So this is a picture of the hot gases that are kind of streaming into the black hole. And today we have enough technology to look at various pieces of data and put all this together and reconstruct this picture, thereby proving the existence of what is a prediction of the Einstein theory of relativity, namely the existence of black holes. There are many other incredible discoveries that took place in the last 10 years or so. And it would be good to also keep in mind that Einstein's theory of relativity, or general theory of relativity, was announced in the year 1915. And many of the predictions are being verified 100 years later. So these are the scales of history in science that I would like to draw your attention to, something to keep in mind, that what we do today, maybe we will not see its implications within our lifetime, or not in the next 6 weeks, or not in the next year. It may well take 100 years for us to see. In fact, Einstein himself did not believe that gravitational waves, which were predicted by his theory, would ever be seen. The reason he did not believe it is he did not think that technology would advance to a point where the predictions of his theory would be vindicated. These predictions of his theory would be vindicated. So you see, science also doesn't just progress on its own. It also progresses because of technological influences. There's a feedback between science and technology, and one drives the other. So some years ago, there was a conference at the national, at the American NSF, which was live streamed. And in our building in Bangalore, we actually watched the live streaming of the announcement of the gravitational waves. And there was this person, David Reitze, who was the principal investigator of this project. He was so excited when he entered the room. I mean, they didn't say that we are going to announce that we have seen gravitational waves. They just said there's going to be an announcement, but it was written all over his face, and he just couldn't contain himself, kind of jumping up and down. We did it, we have detected gravitational waves. So this is an incredible thing. And the planning of the gravitational wave detectors also took many decades and very great advances in technology before we could unequivocally say that, look, we have detected these gravitational waves. So as I already said, this came from the prediction of the general theory of relativity, and it came from the merger of two binary black hole systems of masses 36 and 29 solar masses. Now, I'd like you to just keep an eye on these numbers, a little bit of mental mathematics while you're at it, and it just adds up to 65 solar masses, but the new black hole that formed was only 62 solar masses. So I ask you, what happened to the other 3 solar masses? Went into energy. It went into gravitational radiation, which basically shook the fabric of space-time. We have to think of what amazing things these are, what the human mind is capable of, and how many generations have worked on such things before, you can make a discovery like this. And of course, it's also the task of scientists to explain to the public what is being done with public money. So all these activities, such as having, a press conference, or the talk that I have been asked to give, is a way in which we give it back to society that we are being supported by the taxpayer. We have to explain to the layman and to the younger generation what it is that we've been doing in the decades the taxpayer has supported us. There are a few more examples that I have over here. It's not just, black hole systems mergers that have been observed in the last 6 or 7 years. Many other, cataclysmic events have been observed, such as neutron star mergers. Then now you all know that India is also going to be a member of this consortium of observatories across the world. And our participation will be called Indigo, and we will have a station in Maharashtra. And this particular experiment has many different stations so that you have a proper triangulation of the sky, and you have much better directional information when you see mergers of black holes or neutron stars and so on. And it's not that Nobel Prizes are important, but Nobel Prizes today, again in human history, are sort of milestones which recognize scientific achievements. So I'm not saying that everybody here should think about Nobel Prizes. It's just something to keep in mind, that this is a way in which such ideas are honored. And the people who are honored with the Nobel Prize for this, there's one theorist, Kip Thorne, and 2 others, Rainer Weiss and Barry Barish, for their contributions to this. And they worked over decades and decades. And that's the astonishing thing. So these are the 3 people who are associated with black holes. Somehow my talk is a little black hole oriented. It's just so. It doesn't mean that other branches of science aren't so important. So this was Albert Einstein when he was a young man. There normally one sees pictures of him only when his hair had turned gray, but that was him, and he was rather young around the time he actually did the special theory of relativity. I think that's a picture. And Carl Schwarzschild, who a year after the general theory of relativity had already found the Schwarzschild solution, which is a static black hole. And then the spinning black hole solution was given much later, several decades later, by Roy Patrick Kerr, who's actually even recently had a paper on the archive. So, so we are actually looking at the entire history of science when you look at pictures of people like this, except poor Schwarzschild, died soon afterwards after his paper, because he got some infection out in the front and didn't last very long. So when we think of people like Einstein, there are very great romantic stories about him. Naturally, he's one of the most towering personalities in science. But then, what were his thought processes? So one of the things that I want to talk about in this hour that I'm going to spend with you is to go into the psychological aspect and the thought processes. What kinds of things did these people think about? It's all very well to say that he was the most brilliant man who ever lived and all that, but it's far more interesting to ask and to figure out what it is that he was thinking about and how did he think about these things and what did he say. Of course, he's not there now, so we can't ask him. So we can only go back and read some of the things that he wrote. For instance, as far as the principle of equivalence is concerned, these are the simple words that he said about how he got inspired to think about, formulating the general theory of relativity. You see, he was German by birth, then he lived in Switzerland. He went there to school, and then, of course, he didn't have citizenship for a while, so he didn't have a proper job. So he had to take up a job as a patent office in Bern. And he did science on the side, you see. And you see many pictures of him standing like I'm standing in front of you, because he was probably not given a chair, because they didn't want the patent officer to fall asleep. They had to stand and inspect all the patent applications and so on. But later he says, I was sitting in a chair in the patent office at Bern, when all of a sudden a thought occurred to me. If a person falls freely, he will not feel his own weight. I was startled. This simple thought made a deep impression on me. It impelled me toward a theory of gravitation. That's what Albert Einstein says. Now, I must also say that there's a person, Patrick Winston, who is a theorist of talks, how to give talks. So he says that we all have only one language processor, which is either we can hear what the speaker is saying or we can read whatever is presented. So I violated this rule over here. But I give you a choice. Either you listen to what I'm saying or you read, but you'll also discover that these words are true. You can't do both at the same time. But some of the material that I'm talking about, unfortunately, forces me to have a rather heavy slides over here. Chandrasekhar, who is one of the, again, great scientists who was born in India, but did much of his work in England and later in the US. He also had something to say about the scientific process. Now, he led a long life and he was productive almost till the end. He was a person who had worked very hard through his life besides his research. He was also the editor of the Astrophysical Journal for many, many years. He would often referee papers himself. And he's written several very fat books on all sorts of topics like radiative transfer, on ellipsoidal shapes, so on and so forth. He used to work like 12 hours a day, I think 7 days a week. Not sure about that, but at least 5 days a week. So he says, in some strange way, any new fact or insight that I may have found has not seemed to me as a discovery of mine, but rather something that has always been there and that I had chance to pick up. This is, of course, a very humble way of talking about it, because, his discovery of the Chandrasekhar limit, it's not like it was just out there. This was in the early days of quantum mechanics. People didn't understand all this Fermi-Dirac statistics and all very well. So he took it and he applied to the interior of stars. You have to imagine what all things he must have thought about in order to actually arrive at this particular conclusion. So in this adventure of science that we are all participating in, there's a large variety of scales. And it's nice to remind ourselves of what these scales are and where they start from. So you can start with the quark, which is the smallest scale that is shown over here. The quark, which is sitting over here, which then sits inside protons and nucleons, sitting inside a nucleus, which then sits in silicon dioxide molecules, which then sits in a sand grain. And here's a human foot. And you can start seeing the scales over here. Here, the one appears after something like 15 zeros, that's a femtometer, and the length scale grows. And the laws of physics are supposed to hold at all these scales. You see, what an amazing thing. So here is 1 meter. I don't know whose foot is 1 meter, but anyway, this says that this is 1 meter. I think that's the diameter over there. So this is 1 foot. So it's 1/3 the length, I suppose. Now you also have to think that biology is essentially at the scale and at the scale, at the level of human beings, at the level of microbes, the level of the earth. And today we also think of the earth itself as a system. you have something called Gaia hypothesis, whether you like it or not. It's a hypothesis that we're considering as if the planet Earth itself is a living organism which all hangs together, that makes human life possible, that makes it possible for all of us to sit here. And the Earth itself, of course, is moving around in the solar system like so, rather close to this medium-sized star. And here's Jupiter, which is represented by a much bigger object, which then sits in the Milky Way. And then the Milky Way is, of course, sitting inside the local cluster. And all these galaxies are sitting in the cosmos. And the cosmos also has the cosmic microwave background radiation. So it's not just all imaginary stuff, but we actually have the laws of physics that we can study and learn and check at all these scales. For instance, the talks that I heard today had to do with evaluation of processes associated with these tiniest length scales. That is what our school is about evaluating Feynman integrals, which has to do with the interaction of elementary particles. But it also turns out that some of the diagrams and mathematical objects discussed by Professor Stefan Weinzierl also show up in the theory of gravity. So, it's a beautiful enterprise where we have created all this wonderful mathematics to study physics at all these scales. Another topic of interest to us at the school is what is called the Higgs boson. The Higgs boson was something that was predicted to exist in the year 1964, a very good year, I might add, for reasons that I will not tell you. So it was predicted in 1964, and it was discovered only in the year 2012. It took almost 50 years for it to be discovered. So there's an equally exciting story where, again, there was, a wonderful press conference, and people who proposed the Higgs mechanism, Peter Higgs, and one of the others, Francois Englert, were all present. And then there was a worldwide media event where the Director General of CERN welcomed the gathering. And the present Director General, Fabiola Gianotti, was one of those who gave the talks, along with one of our colleagues from the other collaboration. They announced the discovery of the Higgs particle. You see, it's quite a story. It's like a detective novel that is unfolding in front of our eyes. The subject of elementary particle physics, the predictions, the confirmation of those predictions, and the further studies of the properties of these particles and so on. So what I do, obviously, when I'm standing here and I've claimed that the taxpayer has supported me all these years, I owe it to you to explain what it is that I do. My own field, which fits into the rubric of the school, is elementary particle physics and field theory. And we work on something called the standard model at high precision. It's an extension of the quantum theory of electrodynamics, which also takes into account the weak interactions, which are responsible for, let's say, medical isotopes, so responsible for radiocarbon dating and so many other phenomena, and also the strong interactions, which keeps the protons bound. I have worked on many problems over my long years. More recently, there's a particle called a muon. It's a heavy cousin of the electron, which has a spin, and it precesses in a magnetic field. So the rate of precession of this muon is something that can be measured at high precision, which is also sensitive to the properties of the quantum mechanical vacuum. So you have to be able to compute what it adds up to in theory and compare it with the experimental measurement. So this is a very difficult and problematic calculation, and I have some contributions in this particular field. And most recently, along with some of my very brilliant students and brilliant ex-students, I might add, there's one ex-student and two students over here. Brilliant students, please put up your hands. Well, they are very modest. They're not going to put it up, because without them, I wouldn't have been able to do any of these. But later, you can identify them. Each of them has a halo around his head, and you know who's the brilliant guy out of those. So just as in the rubric of the school, it's a mathematical methods, requires very sophisticated mathematics. I'm not sure mathematicians will agree, but certainly amongst ourselves, we agree that the mathematics is sophisticated. So we need to improve these methods. And I've also participated in many ways in planning for future physics at future accelerators. And the taxpayers' money, we all sit in the only national committee in which I serve, where we direct the activities of Indian scientists and they go and work in CERN. So here is an example of one such discovery that we made, or one we used mathematical methods to evaluate certain objects called n-fold Mellin-Barnes integrals. And this was done by myself and two former students, and Samuel Frio, who has been a long-standing collaborator. He's an expert on these topics in Australia. So in addition to actually developing these methods, we have also developed packages that we have made available to the entire scientific community. They're all open source softwares, which can be downloaded by any user, and it can be used by them to address any problem that, that is of interest to them. This is not just us, although I must say probably in India, we are one of the only groups who does it. And there are major groups in Germany, and we have several experts here who have spent many, many decades, putting forward such useful packages and softwares for the use of the community. What is all this good for? This is a question that you might ask. It's not a question that you might ask, but this is a question that was asked of a person called Robert Wilson, who was the director of Fermilab, one of the most important American laboratories. He had also been a member of the Manhattan Project, about which you must have heard recently because of the movie Oppenheimer. So anyway, so Robert Wilson, of course, as a public servant like everybody else, he was asked to appear in front of a US Congressional Committee, which was chaired by kind of a really very difficult senator. Senator Pastore was his name. So Pastore could strike fear in the hearts of anybody with his kinds of questions that he would ask. It was not just restricted to bullying physicists. He would bully anybody who had to appear in front of him, because that was his job, because he had to decide public funding. So Pastore asked Wilson, what is all this good for? And he said, does it have anything to do with the defense of this country? So Robert Wilson gave one of the most amazing replies, which is etched in the collective memories of anybody who reads about scientific history. So when asked, does this have anything to do with defense? This is what he said. Only from a long-range point of view of a developing technology. Otherwise, it has to do with, are we good painters, good sculptors, great poets? I mean, all the things that we really venerate and honor in our country and are patriotic about. In that sense, this new knowledge has all to do with honor and country, but it has nothing to do directly with defending our country, except to make it worth defending. So these are like pretty amazing words. And this was told to me by a friend about 25 years ago. He's no more. But you see, when you hear these things from somebody, it could be even someone like me, these things will stick in your mind. And although that's the only time I heard it, I always kept this in mind whenever I'd be asked, what is it good for, what you're doing? Now, all the examples that I've given you somehow suggest that it has to be some large, enormous experimental facility where hundreds of people have to work together, very sophisticated instrumentation. Well, that's partly true. Vedango works in such a place. Most all his work comes from the Large Hadron Collider at CERN. But even now, there is a lot of science that can be done at the tabletop. And we've had discoveries in the past 15, 20 years, such as, or already more than 35 years, high TC superconductors. We've had the discovery of graphene. There are things called topological insulators, which condensed matter experimentalists have found. But all these have been made possible essentially by advances in technology, and also the human factor, where the scientist has to apply his or her mind to see what to discover. How do I do the best with what I have? So the sorts of things that we do with paper and pencil and computers also the same way. Today, everybody has a computer, everybody has software, everybody can download this or that. But what do you do with it? So that's where you come in, where you put all these things together. But it's definitely worth asking, what is the role of the individual? So let us see what others have said about this interesting question. So I'm not going to quote myself, there's not much to quote, but I'll quote other very important people who have things to say about these issues. So what do the protagonists say about this, about their scientific, why do they do it? What's the key message? There's also, of course, another struggle always in science. And there is a school called reductionism. Steven Weinberg was one of the important prophets, I might say, of reductionism, that you have to find out the most basic laws of nature, so to reduce it. But he also does admit that there are collective phenomena, even if you understand the basic laws. To look at macroscopic properties, you will have to put these elements together, and that's what gives rise to synthesis. So there's always a struggle, which every one of you will also find as you stay in this field, as you grow, as you work in this field. In your mind, you will have to sometime reduce your problem to the smallest building blocks. Later, you have to put them back together and get the full solution. So mathematics is one of the simplest things to give examples from, because you can explain problems to any child, and of course, you can't explain the solution even to adults. So one such example, how many of you here have heard of Fermat's last theorem? Fermat's last theorem? Anybody? There's only one guy who's heard of Fermat's. There are two. Now I see more hands going up. Very good. So Fermat was a judge, and he in his spare time used to do mathematics. Now this again gives the idea that to do anything important, you must have a job somewhere else, the patent office or be a judge and so on, and then do things on the side. Well, today science is a profession. It wasn't always the case. In Europe, science became a profession only towards the end of the 19th century, 20th century. It was, of course, flowered completely. So Fermat, of course, as you all know, was looking for a generalization of the Pythagoras theorem. Pythagoras theorem, we all know, 3 squared plus 4 squared is 5 squared. He was asking for integral solutions when the exponent is not 2, but the exponent is 3, 4, 5, 6, 88, 9,000, whatever. And Fermat claimed, and he wrote, that he had found a proof that it is not possible to find any solution except for n equals 2. And there's a lot of work in the 19th century especially, where for many special cases, Fermat's last theorem was proved. I think people like Kummer had done a lot of work in this particular problem. But the statement of Fermat is that this is true for every single exponent. It doesn't matter whether it's 8 million or 8 million raised to 8 million or 9 million raised to 10 million. For every single exponent, it has to be true. And this was not solved. There is an important mathematician, Gerd Faltings, who had a theorem in the 1980s where he proved that if Fermat's last theorem is violated, it's at most for a finite number of cases. Okay? So that is already a huge step. He had reduced it from everything to a finite number. Then along came Andrew Wiles, who was already a very well-established and famous mathematician, famous number theorist, who had a childhood dream. It's very important to A, have a childhood, B, to have a dream, and C, to have a childhood dream. So Andrew Wiles and his mother took him to the library where he read a book about Fermat's theorem. And then he told himself that someday he's going to prove Fermat's last theorem. And the reason he did it is some people had proved some steps in the path of the proof to Fermat's last theorem. So these names are associated with Japanese mathematicians, Taniyama and Shimura, immediately after the Second World War. Now, these are all people, and if you read about their lives, it's very impressive and sad at the same time, because soon after the war, many of them, they had a very tough life. They had almost nothing to eat. Still, they were doing mathematics on the side and so on. So they came up with a certain conjecture, and this had to be proved. There were, again, various steps in this process, which people had proved. And finally, it left to be proved that this conjecture of Taniyama and Shimura had to be true. And Wiles actually did this. It was a very exciting story. And there are at least 2 popular books written on this, one by Simon Singh, another one by somebody whose name I've forgotten. And he gave a very long and beautiful interview to BBC where he talks about his Eureka moment, what is called Eureka moment. There's another example. As I said, mathematics is one of the more easy subjects to introduce. And this is called the Poincaré conjecture. It's named after Henri Poincaré, who was called the last universalist. So Poincaré is also very important in physics, besides being a mathematician. We call the symmetries of space-time in his honor as the Poincaré group. There are so many things, the Poincaré cycles in the about motion of planets and celestial mechanics. And there's also the Poincare conjecture. He was the founder of the subject of topology. So he had a particular conjecture. Again, mathematicians are very good at giving conjectures. I suggest you also make some conjectures. Maybe you'll become famous too. I think I should also try one. Ravi, you should also have a conjecture named after yourself. So anyway, so he had a certain conjecture about the smoothness of surfaces in various dimensions, and all dimensions were settled except the case of 3 dimensions. And here was this Russian mathematician, Grigory Perelman, who used again physics methods, which were developed by Richard Hamilton, and many came from properties of renormalization group flow of coupling constants in the nonlinear sigma model. And these are all words, but at least for some of the members of this audience, very interesting that from a completely unrelated field of physics, there were ideas that percolated into mathematics and then were used by Perelman to, solve one of the most outstanding problems. So this was one of $1 million prizes, and Perelman turned down this prize, and he also turned down the Fields Medal. This is what makes mathematicians very romantic. They never do anything the way anybody else does. I also try to be eccentric, but I haven't become great. So, I don't think the causation works in the other direction. There are also other related subjects today, theoretical computer science. So far, nobody has been able to explain to me what is the difference between theoretical computer science and mathematics. But anyway, they claim that some problems belong to their domain, although it looks like mathematics to me. There's something called the Cadison-Singer problem. And this is the point that I want to draw your attention to, which is an outstanding problem for a long time. And these are related to something called Ramanujan graphs. How many of you heard of Ramanujan? Ramanujan, anybody? Everybody has heard of Ramanujan. Well, the most amazing mathematician who, of course, came from India. And as usual, tough and romantic life, died at the age of 31, pretty dreadful. But you see the ideas of Ramanujan, which are more than 100 years old, or ideas somehow spawned by his work, even today are being used to solve current problems that were in unexpected connections. Oops, went the wrong way. Yeah. So anyway, these are a few words about this Cadison-Singer problem. I don't want to say much more than this. It was recently solved by these 3 authors, Marcus, Spielman, and Srivastava. So Srivastava used to be at Microsoft in Bangalore, but I think now he's gone. Now, I don't want to go away giving the impression that great science is done only in mathematics and physics and computer science and related subjects. It's only because I happen to be in this field. I don't believe in parochialism and territoriality. So there are such great discoveries, inventions in so many other subjects. And those who work in those fields, and even those who are outside it, who have an informed layperson's idea of these subjects, if you think about it, then you are amazed at how great such things are. The theory of evolution, for instance. Now we all take it as an article of faith that it must be true. But when Darwin started, and he had to put together many pieces of evidence to come up with a simple theory of evolution, which is, of course, founded on a couple of principles, which is that of chance mutation and survival of the fittest. To a first approximation, that's what it is. And you can actually see some of these predictions in real time, for instance, in Madagascar, which is considered as some kind of a gene factory, where many species evolve very fast because of very peculiar topography of Madagascar. They actually see these things in real time. You can also do this in the laboratory with fruit flies and hamsters and rats and so on and so forth. Look at the theory of evolution. If you think of Gregor Mendel's theory of genetics, I mean, here was this priest in Austria who had this idea of doing these experiments with peas and crossing peas and so on. It's not just about doing experiments, it's about thinking about the results and trying to see, is there a pattern, and to arrive at essentially the correct reason why the phenomena are what they are. I consider, well, this is my opinion, as one of the very, very great breakthroughs in biology is the theory of genetics. And this was at a time when he had no molecular basis. The idea of chromosomes and inheritance. Everybody knows that they inherit traits from their parents. but you don't know. Very often people blame their parents also for everything that's wrong, but I'm not talking about that aspect. I hope you young people don't do that. Please thank your parents for everything that they did for you. Well, that aside, but to think that there is a unifying scientific principle that he could derive from his experiments is an astonishing thing. There are other amazing discoveries like continental drift. Who would have thought? Today, if you take the various, shapes of continents and you do a cutout and you fit them, then yeah, sure, yes, there may have been a proto-continent which broke apart. But whoever came up with this idea, you have to think what an amazing leap it was. And to also explain things like, the rise of the Himalayas with plates colliding and raising and so on. Because these are not things that are happening at the human time scale, right? They happen over thousands of years or millions of years. But the human mind is capable of doing this and applying it to phenomena around us. The ice ages, another great discovery. The last ice age, which ended about 15,000 years ago, had lasted 100,000 years before that. We are now, believe it or not, we are supposed to be in a warm interglacial period. The next time there's an ice age, even in Madras, the weather will be good. But anyway, we'll leave that aside too. So you see, the human mind is capable of dealing with all these incredibly complex ideas and notions. And today we also know how climatic change is associated with the various motion of the Earth's orbital parameters, such as the planarity, the eccentricity, the nutation, and then the drift of the Earth's axis, are all capable of giving rise to cycles. And this is called Milankovitch cycles. You have to go back and think, what is it that Milankovitch did that he could figure out these things? So on, there are so many other examples. Pasteur's theory of microbes, that diseases and beer and yogurt can have the same underlying basis, right? So, these are all the amazing discoveries of the last 2 centuries, I would say, which has made modern science possible and make the world what it is. There are also many others which are a little more abstract, such as Shannon's information theory, which is considered really breakthrough, which has made the modern internet revolution and the electronic revolution and so on possible. Now, you people shouldn't go away thinking that everything was done by men. It's not true. Of course, women have had a position which has been inferior because of historical reasons. So many of the almost all the examples I've cited is really because of men, but there are other, of course, outstanding discoveries. If you go back to archaeology, then archaeologists will tell you that agriculture was found by women because they are the ones who used to experiment with various plant species and do selective breeding, or even metallurgy and, let's say, clay modeling. All these things were done by women because men were out working in the fields or hunting animals or whatever. So, they don't get their due, so to speak. But there are some in the modern era who we can immediately identify. Ada Lovelace, for instance, is often viewed as the founder of computer science. Emmy Noether, a very towering figure in modern algebra. She didn't even live very long, probably only about 40-ish, maybe a bit more. Then Marie Curie, you all know her, the discovery of radium, only person to have won 2 Nobel Prizes in science. Now, do you see the answer to my second slide? Does anybody see the answer to my second slide? That was Cecilia Payne. She's a very important person who analyzed the stuff that stars and the universe are made of. Because at the time she was doing her work, people believed that the abundances in stars of matter was similar to that on the Earth. So she's the one who proved that it was primarily hydrogen and helium. So, really, really remarkable discovery. Julia Robinson, a very famous mathematician, and she did the most important work on the path to solving one of Hilbert's problems. Hilbert is a name which will keep appearing in my talk. In the year 1900, he listed 23 problems, which he said would define the direction of mathematics, at least for some years to come. So they are numbered 1 to 23, obviously. Some of them were very trivial. Some of them are still not solved, including the Riemann hypothesis. And some of them took a long time to solve, such as the 10th problem, which took about 50 or 60 years to solve. So this had to do with looking for an algorithm for solving certain Diophantine equations. And Julia Robinson and some other co-workers showed that it is undecidable. So there's a story about how the person that she was corresponding with was in Russia, and they would have to write letters to each other. See? Now today you send a WhatsApp, and within 2 seconds, your mother doesn't answer. You call up your mom and say, "Did you get my WhatsApp?" It's a little different in those days. See? So some other examples, the discovery of dark matter is attributed to Vera Rubin. There were some ideas from Fritz Zwicky already about the existence of dark matter. But anyway, it was conclusively established by Vera Rubin. During my long suffering years as the chairman of the center in Bangalore, one of the high points was I got to have lunch with Jocelyn Bell. It was associated with the discovery of the pulsar. She's a very wonderful, nice person, totally unassuming. So that was a high point of my chairmanship, was to have lunch with her. Lunch wasn't very good, but I'm not going to tell her that. Yeah, guest house lunch. Many other names that you know. Here is a list. I could go on and on. There is Rosalind Franklin and the double helix. Miriam Mirzakhani was the first person to win the Fields Medal, first woman to win. More recently, Marina Vyazovska. Today, one of the leaders of the most important science lab, Fabiola Gianotti. I think she's even got a second term. She got a second term? Yeah, there you go. Then Donna Strickland and Andrea Ghez, they won physics Nobel Prizes. There were a couple of chemistry Nobel Prizes this year. And a year or two ago, maybe already 3, there's a remarkable Nobel Prize in biology, which was given only to women, and that was Jennifer Doudna and Emmanuel Charpentier. So this is an era when women are actually going to flower, and it's not going to be a situation of, of being left out. And I think this is a very welcome development. I want to say a few words about our own country. Many names are already known. However, there's a shortage of role models, so to speak, because many of the figures who are talked about are people who have already been gone for 50, 60, 70 years. But their names are, of course, very well known, because this is, again, history of a developing country, which was formerly colonized and so on. Some of the great names are actually associated with the colonial period, with all its drawbacks. I mentioned Ramanujan's name already. He's like a priceless, inexhaustible wonder, the work that he did. And then it just shows up everywhere all the time, even in these Feynman integral calculations. There'll be something, they'll say, "Oh yeah, Ramanujan had a formula for this." And you go and look, sure enough, it's there. His lost books have been recovered. They have been edited, compiled, cleaned up. There are volumes and volumes. Here's a man who died at the age of 31. How did he do so much work? This is not to say that everybody needs to be a freak of nature. He certainly was, for the lack of a better word. Some people have objected to the word freak of nature. Should not be viewed as a pejorative word, but it really is true. Somebody who is like 50 sigma from the mean, what else can you call him? A freak of nature. And of course, you all know the name C.V. Raman, you know the name Meghnad Saha, Bose and Bose statistics. Bhabha, of course, this hall that we are standing in, named after him. Did the atomic program for India. Sarabhai, who did the space program. There are many others who are known in their fields. Rai Chaudhary had his equation for the cosmos itself. Then G.N. Ramachandran, I don't know how many of you heard of him. G.N. Ramachandran, anybody? So this is on the path to the double helix, here an important contribution. And the thing that I want to emphasize here is that most of this was work done in India, There were others. For instance, there's a person who established nuclear physics in Andhra University. He had gone to Germany and he had worked with Max Born, and he came back here and he established a school of nuclear physics. I've forgotten his name. Many others who went to these places and came back and did science, often forgotten. And we need some historians to work on this. Rajendra Singh, who's a professor in Oldenburg in Germany, is an expert who's writing a lot of books on Indian scientists and so on. So it's a very commendable effort. So it's not just India, other countries, especially Germany, are interested in supporting this kind of activity. There are some other names that may be known to you, may not be known to you. Birbal Sahni, he established paleobotany in India. There's another important woman, Janaki Ammal. She started this field called cytogenetics. This guy's getting tired. I'll finish in 5 minutes. There are other names associated with number theory. Ram Prakash Bamba, he is a good 95 years old, and he's still with us and still does Sudoku puzzles in the morning, the father of our friend Bindu Bamba, of course. Then there is Sarvadaman Chawla, who went off to US. Harish Chandra is another very towering figure. He was an alumnus of the Indian Institute of Science, and then later went to the US and worked with the Institute for Advanced Study. It's incredible the kind of work that they did. Of course, in our own field, we have George Sudarshan and Abdus Salam, who came from India and then went and worked in other places. There are many books on these people that you can go and read. Just want to mention a couple of recent interesting problems. And there's a site called Quanta, which is a very interesting website where there are always very exciting stories about mathematics and physics and most recent developments. Of course, we don't know how many of them will withstand the test of time, but they are very nice stories about. There was a story which appeared in the New York Times, which is called the Euler Spoiler. This is about 40 years ago, or maybe 50 already. So these authors, Parker, Bose, and Shikhande, they actually disproved one of Euler's conjectures about Latin squares. So these, I think, Shikhande and others, they were not really professional mathematicians. They knew something and they worked in small places and still did this. Recently, the IIT Madras group has done some very interesting work on quantum entanglement and so on, again associated with Euler. Because Euler is everywhere, even though he lived, I don't know how many 100 years ago. And one of our mathematics colleagues recently gave a partial solution to one of Hilbert's problems. So in the last few minutes, let me talk a little bit about the psychology of creativity. Obviously, I'm not the one who first thought about this. Many interesting and important people thought, how does one go about science? What is this process by which science is born? So some of the important ideas came from Jacques Adamar and Helmholtz, of course. Helmholtz was a professor, I think, of physics, physiology, and law, something like that. He had 3 or 4 positions, the same person. He also invented the ophthalmoscope, besides inventing his coil and besides inventing his equation. So not bad for a lifetime. And he also spent a little bit of time thinking about the psychology of science, of discovery. So they gave a system of processes through which science actually emerges. And this, it's again common sense if you think of it, after somebody else has put it in perspective. So Adamar also is very famous, as you know. He's the one who proved the prime number theorem. There are matrices named after him, Adamar matrices. So they say that there's a period of preparation, which is true for all of us. You have to think about a problem hard. You have to develop the tools that are needed. Then there's a process of incubation where the idea takes seed in your mind, and then your mind is working on it. And then finally, you get this so-called aha moment, which is that of illumination. But that's not enough. Whatever you think is an answer has to be verified, because in science, unlike in other human activities, falsifiability and verification are extremely important. Okay, so already Helmholtz and Adamar had talked about this. So we can have examples like this. For instance, Planck came up with this formula where he already had an idea of how to resolve this famous conflict in blackbody radiation, the formulae of Wien and Rayleigh. And then he came up with his formula, and then he had to give the theory of how that formula came about. And he, of course, also had to introduce this constant, the Planck constant. And he wrote a letter, he told his wife that today I've done something incredible. I have actually used the new constant of nature. You see, he knew in his mind that it had been some astonishing breakthrough. Others have also talked about their eureka moments. We talked about this process of illumination and, these steps that we talked about, which is preparation, incubation, and illumination. Poincaré talked about a remarkable experience that he had. He didn't have very good eyesight. So I think this was a problem that he had. So probably he had to do a lot of thinking in his mind. He also had a very famous cousin who was the Prime Minister of France during the First World War. Not a very enviable job to have, Raymond Poincaré. So anyway, he does describe his eureka moment about solving certain problems, which is called the Fuchsian systems, how he was stepping into an omnibus, and then suddenly a problem on which he was working on for many years, he suddenly got the answer. Kekulé, all of you know the story of Kekulé. Once when I went to Bonn, I saw somebody holding a statue of somebody holding something in his hand, some round structure. I was wondering what on earth is that. Then I saw that it was Kekulé. What did Kekulé figure out? My friend is falling asleep. That's why I'm asking you. Benzene ring. He found it. So that statue in Bonn was that of Kekulé holding the benzene ring. So of course, at that time, they had no idea that you have this kind of, there are two kinds of organic molecules, right? Those which are just chains and those which are aromatic compounds which have a benzene ring. So he talked about how he figured out the structure when he fell asleep in front of a fire and saw a snake gobbling up its own tail. It's a beautiful story and it may well be true, or maybe he was hallucinating. Doesn't matter, he still got the answer. Planck also talks about his discovery of quantum mechanics. He also made some observations about our role as human beings in this cosmos. And many of us, of course, work for this moment, which may or may not come. Now, I'm only quoting people from 19th century or early 20th century. How about more recently? So this person I talked about, Nikhil Srivastava, I should also quote people who are younger than myself, not only people who are like 3 generations away. So this guy obviously is much younger than us. So he says that he does not believe in being a mega workaholic, and he gives a formula. Now, you please don't read this selectively, okay? You have to read it in its entirety. He only says short spurts of highly focused work, but he says you have to go after a problem. And he also says something important, that sometimes you realize that you have tried everything possible and you're not going to get the answer. Just move on and go to the next problem, okay? This is kind of very practical advice, which is also useful. Venki Ramakrishnan was a Nobel laureate in chemistry, has also talked about this. He was also president of the Royal Society, and he has come to India several times after the Nobel Prize. So wherever he went, the newspapers would, of course, corner him and interview him and so on. So he has talked a lot to the press. So he makes these observations that it takes courage to tackle very hard problems in science. And he also makes some very beautiful observations, which is very important for Indian parents. He does not want science to be converted into a contest. You have to enjoy what you're doing. It cannot be cutthroat competition here. In this regard, there's the anecdote of Heisenberg and his brother. So Erwin and Werner Heisenberg, their parents made them compete a lot with each other when they were kids. And the two brothers in their later life could barely even talk to each other, you see. So this is a bad habit, not just with Indian parents, but parents everywhere in the world. But today, of course, we know better than to do such things. But Venki Ramakrishnan makes another important point, which is that he talks about the importance of multidisciplinary training and taking ideas from many other fields, and also emphasizes the importance of hard work. Weinberg also has pieces of advice for all of us. And Weinberg is, as I've already termed him, a prophet. So obviously all of us have listened to what prophets have to say. So he makes some very interesting and important points, which young people here have to keep in mind. He says, no one knows everything. And so you do not need to know everything to start research. Just do it. Then he says, aim for rough water, by which he means don't work on safe problems, where you just take a well-known thing and just make a minor extension. The third one, I'm not so sure, but this is what Weinberg says, forgive yourself for wasting time. And the last one I agree with, learn something about the history of science, because that really puts things into perspective. Why are you doing what you're doing? Just the last few words for the young people over here, since this is an institution where you are all going to be the next generation. Please keep these things in mind. This comes from a long talk that I once prepared on communication for students, and just giving you in bullet form. Communication skills are very essential, and learning to write research papers And today we have multiple modes of communication. It's not just writing papers. This is also an act of communication. We have social media, we have all these things. You can use these things effectively. I have seen many American scientists, announcing their most important papers on Facebook. Why not? It's just as good a way of communicating as mailing preprints to somebody. So one should not be shy of, I don't know about Instagram and Snapchat, but definitely, LinkedIn and things like this is a good way of communicating. And it's also very important to impart information in all human modes of communication, speaking, writing, and any other kind of medium. And this is going to become even more important in the future. I'm not talking in a crude way about marketing, what you're doing and selling and so on. It's very important because everybody is short on time. So you have to be able to explain clearly and properly what you're up to and precisely. There are also other creative processes in human life. It's not just science. And this is a totally unexplored domain, at least in India. These communities hardly speak to each other. C.P. Snow wrote a very important essay called The Two Cultures, which was the first half of a book called A Mathematician's Apology, written by G.H. Hardy. So Snow over there says that people in humanities and sciences, they just don't communicate with each other. And he actually goes on to say that many in humanities and so on, a little contemptuous of scientists, view them as technicians and, not so interesting what they're doing. Of course, the contempt today is in the other direction also, which is not healthy. So there are other creative processes. How do they go about it? How do they create new things? So these are all things that in the future we'll have to explore. This will all be directions in neuroscience, look at questions of creativity, of interaction between fields, and so on. And even they today have to use computers. In science, at least every single person who is at the school has to use computers. That era of doing things with paper and pencil is no longer there. And here's a little bit about India, where actually we hardly convey to the common man and common woman what we do. It's very important for us to explain to others what we do and to explain to each other what we do. There are hardly any examples where what was a great discovery in India, who did it, how did they do it, etc., etc. There's only one recent counterexample, is Manindra Agarwal, who was former deputy director of IIT Kanpur. He made a very important discovery along with the students in something called primality testing using computers. So there they have explained how they went about it and how they went to the internet and looked at various theorems and so on, and they were able to prove their result. I have a colleague now retired, Anil Kumar, who has written a very nice essay on how he made a very important discovery, which is called the nuclear Overhauser effect in biological molecules. He was a postdoc in Zurich, and he needed a lot of time on a particular machine, which he was not getting. So he very patiently waited till the Christmas and New Year break. Then everybody else in the lab would be away, and he got about 10 days of time for himself, and he would go up. I don't know how he got the permission to enter the building, and he got enough time and he was able to do his measurements and then actually make his discovery. Oops, the wrong direction. Must all be very worried. Well, I've had a few eureka moments myself, but I'm too embarrassed to talk about it. So those of you who want this PDF file, you can have a look and then read it later. So finally, I just want to say to you all, the young people, who are all, of course, already younger than my daughter. So follow your hearts. Well, my daughter doesn't listen to anything I say. I hope my advice doesn't have the same fate with you all. Follow your hearts. And in my opinion, nothing is more fun than research and discovery, because without you all, there is no new tomorrow. I mean, science, everything will grind to a halt. It does require a lot of patience. It's like running, or more precisely, it's like sprinting a marathon. It's not like sprinting 100 meters, but sometimes it feels like you're sprinting a marathon. The famous words of Edison are: genius is 99% perspiration and 1% inspiration. So if you want to look at some developments of some developing of the ideas that I mentioned over here, I recommend you to this wonderful speech by Richard Hamming. It's there, the transcript where he's giving the speech. There's also a written transcript. Richard Hamming, it's called You and Your Research. So you should have a look at this. And everybody, of course, needs a bit of luck in research. But there's a definition of luck that is attributed to Seneca the Younger. Nobody knows whether it's true or not, but it reads as follows. It says, luck is what happens when preparation meets opportunity. So let me finish soon, the next two slides, that this is what Darwin said. It's a beautiful words. He says that there's a grandeur in this view of life. So he's talking about biology, about evolution and different forms of life. With all its powers, have been originally breathed into a few forms or into one. And that whilst this planet has gone cycling on according to the fixed law of gravity, so there's the reductionist thing, we have a fixed law of gravity. From so simple a beginning, endless forms, more beautiful and more wonderful, have been and are being evolved. So he's talking about the rise of, the synthesis of life in all its forms. So let me end here this time with the Grabstein of David Hilbert, with the words in German, wer müssen wissen, wer werden wissen. Thank you.
Thanks, Anant.
I overshot my time.
We really had a joy of listening to you. It was a wonderful.
This is my pal. Yeah. See, I brought my own audience. I told you, my own chair.
I'm sure everybody agrees with you. It was wonderful and quite a lot of things, thought-provoking, enjoyable. So let's thank him again. I'm sure you have a lot of questions.
Yeah, we'll take them.
One or two questions.
No, as many as there are.
As many as.
Yeah. Those who don't want to hear the questions and answers, of course, free to leave. Yes, yes.
Some mic.
Yeah, I think there's a, I think there's a mic coming. No?
I think that I'm loud enough.
Okay. Yes.
Really good talk. I really enjoyed it. I mean, we all do science because we love it. Although it's nice to have the paycheck at the end of the month.
Yes.
But we all really love science. But it is the scientific community that has devised terms such as hard science and soft science. And you sort of alluded to it and just fell short of saying that. So I want to know your opinion about whether there should be terminology such as hard science and soft science. In other words, should there be a hierarchy in sciences? And if someone in this audience does believe in such terminology, what would you say?
I personally don't ascribe to such philosophies. I think that all subjects are equally valid, and all subjects should be held up to the same levels of rigor and correctness and verifiability and so on. In some places you can't do it, but it doesn't mean that you stop your inquiry just because of that. Supposing somebody says sociology, I mean, it's such a complicated subject, but does it mean that we stop studying society? Does it debunk sociology? No. I mean, it's an important subject, and people will make efforts at various stages in history to make it as rigorous as possible. And it also has developed. It's used in fields like management, for instance, successfully. And it's used by HR departments and so on. Any science can be either bogus or it can be good, right? We know any number of instances of fraud in so-called hard sciences also. We know that, there can be data fabrication. Ultimately, it has to do with human beings. Ethics is a human quality, right? So we believe that those of us who are in a particular scientific field, we have ethical standards, we have methods of self-correction, and so on. Now, if you take things like environmental science in which you work, these are very difficult subjects. How do you do field work? I wouldn't know how to do field work on olive ridley turtles. So and I admire people who can do work like that. Somebody else may say, oh, this guy can do some integrals sitting in his office. and then they may envy me for that particular skill. It has to do with human skills. It has to do with training, with what attracts a given person. I don't know if I've answered your question satisfactorily, but that's my point of view. That everything should be held up to the same standards of rigor internally by peer evaluation and so on. It appeals to me. So that's one of the reasons why I'm in this field. So it probably is something to do with how my brain is wired, that I need to really focus on very small number of problems. And I need to break it up. But the example that's often given, even by Weinberg himself in one of the essays that he writes, that you cannot have something like the Higgs mechanism and spontaneous symmetry breaking and superconductivity if you only had reductionism. That he himself gives this example in a well-known article in CERN Courier, where these two things have to go hand in hand. So again, it has to do with a person's taste in science. Some people like something very idealized in a picture. Somebody else may be very particular about what they're calculating and they're very finicky about these things. Yes. Well, that's the reason why you have a teacher. That's the reason why you have a mentor. That's the reason why you have a guide. And that's the reason why you also have a peer group. In this context, I would think it's very important for students to have groups in which they discuss with each other so that, they have a collective awakening of their interest in particular fields. So this is a question that's often asked. And I think the role of an advisor or a supervisor or a teacher is very important. And today we have all kinds of resources. You have the internet, you have YouTube where you listen to lectures, then you have Quora where you can go and get thoroughly confused, or you can go to StackMath and get even more confused. So there are all sorts of possibilities, but you have to stay calm. It's like anything else in life. You will find your way. This is again in mathematics, they say that there's something called mathematical maturity. That a kid at 12 or 13 is not mathematically mature, maybe very good at solving problems and so on. But someday, unknown to that child himself or herself, the child acquires mathematical maturity, and suddenly they are able to recognize the world for what it is, the world of mathematics. It's true in all spheres, in science, in chemistry also. You're cramming all these formulas about, alkanes and alkenes and esters and so on. But finally, one day, it all makes sense to you. And it's also a matter of time and patience and wait for this to happen. It'll happen. But of course, the prerequisite is work, hard work, study, and so on. Can you stand up so the others can hear you? Yeah.
Were already published, which is ending quest for trying to publish foreign papers. Where is it taking?
Well, we all live in the real world. Every one of us is subject to all sorts of stresses, all kinds of expectations. So it's part of that. It has to do with cutthroat competition across the world, which is the present paradigm where everybody has to somehow conform to the free market, and then you have to, make yourself a commodity. It's very hard for any individual to change all this. So at some stage, you have to accept that this is the world we are living in, and we have to live in this world, and we have to deal with it. This essay of Hamming gets into that question very well. Of course, he's already passed away about 20 years ago, but he's not talking about students applying, but he is talking about How do you survive in science? How do you survive in an organization? He worked in Bell Labs for most of his life. So there's something called the Hamming distance, which is named after him in communication theory. So that's the Hamming distance. So he would catch hold of people and say, what are you working on? What are you working on? So a new definition to Hamming distance was people try to stay as far away from him as possible. But anyway, leaving aside the second definition of the Hamming distance, he gets into this question of how do you select problems? How do you work on them? How to make yourself efficient? How to survive inside an organization? He makes very interesting points. For instance, he says, you shouldn't try to stick out. You shouldn't try to be an eccentric. Some people do that. And he gives examples of people who could have otherwise been very successful, whose career sort of became floundered because of peculiarities in their personal makeup. All these are important things, but it's actually not really suitable for young people, that article, for people a little more mature than you. But I think you're mature enough, you read it and handle it. So this is the world we live in. We can't help it. If you have to survive and exist in this world, competition is a fellow traveler of our lives. At my ripe old age, I'm still having to perform and prove myself every day. It's not very nice, but we have to do it. I am sure you're disappointed with my answer, but what can I do?
Yeah.
Ravi, you're the director of a lab. You tell him. Yeah. Do you have any words of advice to offer? No. Unless you have 50 papers, he won't give you a job, you see. So some more. I don't know when I'll come again unless Vedango invites me again. So. So I prevented poor HM from going home today. So you have to ask a question there. Yes.
Professor, the students are more interested to listening to you rather than, asking questions.
Oh, yes.
Yes.
You have Dr. Dwivedi has joined us from Jaipur. So you have a in front. Yeah.
So you have mentioned that you need not know everything to start with.
Weinberg said that. Yeah.
Yeah, you are mentioning.
Yeah.
Stress you have an idea, but you don't have proper mathematical knowledge to back it up. Is a wasted idea. How to find the balance?
See, it's also a matter of an era. Landau, in his famous school in Moscow, he used to have a theoretical minimum that every student had to learn, do, face exams, and so on. And there's another famous physicist, Gerard 't Hooft. He's a Nobel laureate, the particle physicist. He has a web page on all the things that you have to know before you can start doing research. Now, I can tell you that I don't even know 1% of what 't Hooft is written on that page. You still have to do it because you may find something topical and then you learn the tools needed for that particular thing. Again, this has to do with the issue of maturity, mathematical or physics maturity, where you know that there's a problem and you know how to go about it. You don't know immediately. You have to play around, stumble. Oh, I've seen something. Okay, that's the technique. I'm going to try this. These things come only with practice. There is no other option. So you were asking something, Dr. Dwivedi?
No, Professor. I was only saying that the students are more interested to listening to you rather than asking questions.
Okay.
Yeah, it was so wonderful, so beautiful, such an interesting lecture. So informative and insightful.
I'm turning
First
red.
time, yeah. In fact,
Really turning red now.
Yeah.
Thank you. Yes.
I will complain about the present day, limited. Okay, in science, it's been going down significantly. In places like West Bengal, they say there's a 30% decrease in number of students joining science division.
Yeah.
Kind of that.
Well, we have a friend, Prem Kumar. He's a professor in Wales. You must know him. He's a string theory person. He's the head of the department in Wales. And he said that in front of his eyes, he has seen the decline of mathematical abilities of students in the last 15, 20 years. This is a worldwide trend, and everybody is talking about it. Nobody really knows what to do about it. Probably it's the availability of all kinds of other career options for students. They can become DJs and VJs and fashion models, and that's again the real world. It's definitely a factor, the world economy. Why would somebody want to get into our field? You're 23 when you enter IISc, you're 28 when you leave. Then if you're lucky, then you do postdoc for 6 years or 7 years. And then you're appointed, some low life somewhere. And then you have to teach 40 hours a week. It is now viewed as an extremely difficult and challenging profession. And governments and universities, educational institutions have to do something about it. They have to improve salaries, they have to improve promotion policies, they have to make things easier for people, right? I mean, a person when he or she is 30 or 31, they want to have a family and settle down just like the rest of us. And then you tell them, oh, we want one more postdoc, we want this, that. And industries in India, I'm not talking about other countries, they are not open to people with advanced degrees. You can get a job in a company only with an undergraduate degree. With a master's degree, already partly overqualified. You have a PhD, you're supremely overqualified. It's very different. In Europe, you could do a postdoc and PhD in our area, and you could get a job in a bank, you can get a job in an insurance company, or you can even get a good school teaching job. In India, school teaching jobs are extremely poorly paid. So it has to do with all these factors, And I have seen my students struggling. So what can I say about these things? So this is a real trickle-down effect to the last several years of universities being dismantled. And now with all this online education and all, teachers and all become even less sought after. Students will learn everything from Coursera or one of these various things that is now available. That's the way it seems to me. I haven't studied the subject in depth, but I feel that these are the factors why it is like that. But on the other hand, we also see that there are still enough students, especially in our country with 1.4 billion people. We have always a supply of very good people. There's no problem with that.
It was such an interesting talk, and as I was hearing, I was also noticing that we also have a logo in NISER.
Yes.
And all these discoveries and inspiring things, what if the logo has a black hole?
Yes.
The DNA, the benzene, and the factors.
Fantastic. It's a cosmic coincidence. That's all I can say. Shall we thank everybody for patiently having stayed here?
If there are no further questions, let's thank Ananthanaryan.
Thank you all. Thank you. Thank you. I thank my online friends also for coming. Thank you.
Thank you, Professor. Thank you very much. Thank you. Thank you.
How are you?